You ever get that feeling you've got a brand new, super powerful computer, but sometimes it just lags? Well, today we're going to pull back the curtain and find out exactly what's going on inside your machine that causes that all too common frustration. I mean, we've all been there, right? You've got this processor that's supposed to be lightning fast, tons of storage, but you click something and you get that little spinning wheel of doom. It's so frustrating. But why? Why does that happen? Well, the answer is kind of a hidden bottleneck, a huge challenge that's right at the heart of every single computer. Okay, so let's get right to the core of it. Your computer's brain, the CPU, it thinks in nanoseconds. We're talking billionths of a second. But its long-term memory, the hard drive, that thing works in milliseconds. Now, that might not sound like a big difference, but it means your CPU is literally thousands of times faster. Think about it like this. Imagine a world-class chef who can chop vegetables in the blink of an eye, but has to wait a full hour for someone to bring them a single carrot. That's your CPU. It's always just waiting for data. So this massive speed gap is the #1 problem that all computer memory design is trying to fix. How do you possibly keep a lightning-fast brain fed with information from a library that's, relatively slow? You can't just make a giant, super-fast library. It would cost a fortune and be impossibly small. To get around this, engineers came up with a really, really smart solution. Instead of trying to build one perfect, do-it-all memory, they created a layered system, a pyramid, really, called the memory hierarchy. Each layer is a different trade-off between speed, size, and cost, and they all work together to keep that speedy CPU busy and happy. To really wrap your head around this, we're going to use an analogy that I think everyone can relate to: a writer's workspace. Picture yourself writing a big research paper. You've got a giant library, a filing cabinet in your office, and the desk right in front of you. Each of those plays a super important part in how fast you can get your work done. Okay, let's start at the bottom of our pyramid. This is your auxiliary memory, your hard drive or your SSD. In our analogy, this is the massive university library. It can hold everything, right? Every book, every article, all the data you could ever dream of. It's gigantic and it's cheap, but man, walking all the way over there to grab one book, that takes a lot of time. So the next step up is main memory, which you probably just call RAM. This is your filing cabinet. It's a whole lot smaller than the library, for sure, but it's right there in your office, so getting stuff out of it is way, way faster. You'd go to the library, pull out all the books and research you need for your current project, and keep them in this cabinet. This is where all your open apps and active files live on your computer. And right at the very top, the peak of the pyramid, is cache memory. This is your actual desktop. It's a tiny little space, but it's where you put the exact papers and notes you need for the sentence you're writing right this second. It's literally right there, within arm's reach. Access is practically instant. And that's what the CPU does. It always checks the desk first before it even thinks about going to the filing cabinet, let alone making that long trip to the library. And this shows you the big trade-off perfectly. Cache, your desk, is unbelievably fast, but it's also super expensive and tiny. RAM, your filing cabinet, is that happy medium. And storage, the library, is huge and cheap but slow. The entire system is built to make sure the data you're using most often is sitting on the fastest layers as much as possible. Okay, so we've got these layers, which makes sense, but that brings up another question, right? How does the computer decide what to put on the desk, the cache, and where exactly does it put it? Well, this whole process is called cache mapping, and it's basically the computer's personal organizing system. So, to keep its desk tidy, the computer has 3 main strategies. First up, direct mapping. Think of this as having a specific labeled spot on your desk for every single file from the cabinet. It's super fast to find things, but it's also really rigid. What if you need 2 files that are assigned to the same spot? You've got a problem. Then there's the total opposite, fully associative. This is the messy desk approach. Any file can go anywhere. It's super flexible, but now, to find anything, you have to search the entire desk, which is slow. So engineers came up with a brilliant compromise, K-way set associative. Imagine your desk is divided into a few sections. A file has to go in a certain section, but within that section, it can go anywhere you want. It's the best of both worlds, a really smart balance of speed and flexibility. And it's what most modern computers use. So, this whole system is working great, until it's not. You've opened way too many programs, you have a zillion tabs open in your browser, and your filing cabinet, your RAM, is totally, completely full. So what happens now? Does the whole thing just crash and burn? Nope. Instead, the computer performs this incredible sleight of hand. It's a little bit of software magic that operating systems use to solve this exact problem. It's called a virtual memory. Virtual memory is this amazing technique that basically tricks your programs. It makes them think there's way more RAM, way more filing cabinet space than you actually have installed. How? It cleverly uses a chunk of your slower, but much, much bigger storage drive as an overflow area. It creates this awesome illusion of almost endless memory. And the secret sauce, the actual mechanism that makes this magic trick work, is a process called demand paging. It's what handles all the swapping of data between the filing cabinet and the library, all on an as-needed basis, totally behind the scenes. So, how does this work? Well, when the CPU asks for some data and it's not in RAM, that triggers something called a page fault. The operating system immediately hits pause on the program, zips over to the library, the disk drive, and finds the page of data it needs. Then it finds a page in the filing cabinet that hasn't been used in a while, swaps it back out to the library to make room, and pulls the new required page in. And then, the program just picks up right where it left off with absolutely no idea that whole swap even happened. It's all seamless. So when you put all of these pieces together, the layered hierarchy, the smart mapping strategies, the magic of virtual memory, what you get is a system that works in this incredible, beautiful harmony. All right, so let's just do a quick recap. The whole reason for all this complexity is that huge speed gap between the super-fast CPU and the slower storage. The elegant solution is the memory hierarchy, our desk, filing cabinet, and library. To keep that desk organized, the computer uses cache mapping, which are the rules for balancing speed and flexibility. And finally, when the filing cabinet gets stuffed, virtual memory pulls off a magic trick to create the illusion of more space, so your work doesn't have to stop. See, at the end of the day, it's not about having one component that's the absolute fastest. It's about orchestration. The whole system really does work like a symphony, with every single part playing its role perfectly to get data to the processor exactly when it's needed. It creates this smooth, fast experience out of parts that seem completely mismatched in speed. And that kind of leaves us with a pretty cool question, doesn't it? This amazing system has worked for us for decades, but now we're diving headfirst into AI, massive data sets, and apps that are more demanding than ever. The pressure on this system is just getting bigger and bigger. So what comes next? What's the next brilliant trick that engineers are going to come up with to feed the absolutely insatiable appetite of our future computers? Thanks for joining me on this one.